Hi all, and welcome to part 2 of this tutorial series to create a neural network in JavaScript. If you remember from last time, a neural network is comprised of 3 layers: an input layer, a hidden layer, and an output layer. So today we're going to create these in JavaScript. So if you open up our code, last time we created these matrix functions. They're to, like for example, to add matrices and multiply them and so on. So today we're focusing entirely on creating the neural network. I've gone ahead and written some notes of what we need to do today, so hopefully we will get this right and we'll get it working. So first of all, let's create the class neural network. So class neural network. Create the constructor. Now the constructor needs to take the number of inputs, the number of hidden, and the number of outputs. So num inputs, num hidden, and num outputs. Let's set the private variables, the properties as such. So we'll just give them the same name, just prefix it with an underscore. Num inputs equals num inputs. Num hidden equals num hidden, and num outputs equals num outputs. Now going back to our diagram, remember we have all these weights that are in between the input and the hidden layer. Let's call that weights 0, and we'll call these weights here between the hidden and the output weights 1. So this underscore weights 0 will equal a new matrix. The number of rows will be the number of inputs. So this is the number, this num inputs. And the number of columns will be the number of hidden. So this num hidden. Similarly, weights 1 will equal a new matrix, except that its number of rows will be the number of hidden, and the number of columns will be the number of outputs. Okay. For the weights 0 and weights 1, we'll need to set that. We'll need to update them during our training process. So let's create getters and setters for them. So get weights 0. That's simply return this underscore weights 0. And we'll also want to set that. So set weights 0, weights. Set weights 0 weights. So we can just go this underscore weights 0 equals weights. Right, and we'll do a similar thing for weights 1. Weights 1, this weights 1, weights, set weights 1, this weights 1 equals weights. Great. So we've done this one here. Next, we need to randomize the initial weights. So let's just use that as our next comment. So randomize the initial weights. We've already created a function in our matrix functions actually, where we can call randomize weights on any matrix. So weights 0 dot random weights, and do a similar thing for weights 1. Good, that's that step done. We should probably test this. So go to our other file, the HTML file, and let's go down to where we set up, here we go, to do neural network. So we'll have to create a variable here. So variable nn, we'll call it. And here we can go nn equals new neural network. Now we need to pass the number of inputs, hidden, and outputs here. I think we should set them as constants. So up where we're setting our constants, let's create a section called neural network parameters. Const num of inputs. I'm not entirely sure how many inputs we'll need, but let's just say 2 to begin with. Const num hidden. Again, there's lots of theory behind what number this should be. The higher usually means the more complicated processing it can do. So we'll just start with 5. We can always adjust it later. And const num outputs Now this one I am confident about. We just want one Boolean flag. 0 turn left, 1 turn right. So one output. So head back down to where we're setting up our neural network. Put in these as the arguments, so num inputs, num hidden, and num outputs. So we don't need these matrices anymore, so we can get rid of them. To test that our neural network's constructor is working all right, how about we output the weights? So nn weights 0 dot data, and we'll do a similar thing for weights 1. We don't need this transpose anymore. So open that up in our web browser. Okay, so we have one, for the first matrice of weights is 2 by 3, 4, yep, 2 by 5, that's right. And our output one, our weights 1, is a 5 by 1 with random weights inside. Awesome. So head over to our neural network class. Let's go down and see what we need to do next. feedForward. Now all that means is that we're going to input some information into our network. It's going to feed through it and some output is going to be created. So let's create a new method called feedForward in our class. It will take an input array as an input, as a parameter. Let's paste these comments in here. So the first step is to convert input array to a matrix. That's easy enough. So let's declare a new array. Let inputs equal matrix dot convert. Convert from array. We made this earlier. So we can just put the input array in there, and that will convert it to a single rowed matrix. That's fine. Next one, find the hidden values and apply the activation function. Okay, to find the hidden values, we can look at this diagram here. You can see that each hidden neuron is made up of these weights, one coming from each of the previous inputs. So to calculate that, it's just the first input multiplied by the first weight, plus the second input times the second weight, times the third input, plus the third input times the third weight. And that can be handled using a matrix dot product. We have a function for that as well. So let hidden equal matrix dot dot, which takes two matrices. The first one being the inputs, and the second one will be the weights, which we all have already determined. It's been randomly determined. So weights 0. Okay. Now the activation function is simply, well, with lots of neural networks, the activation function is something called a sigmoid function. Let's take a look at that. Now, a sigmoid function is simply this, 1 divided by 1 plus e to the minus t. Now what that does, we can input any value into this system and it will return a value between 0 and 1, no matter how big that value is. So if we put 1 trillion into this, it'll output a value close to 1. Okay, which suits our needs very well. So let's go ahead and create a function down here, just outside our class. Function, we'll just call it sigmoid. Sigmoid, it'll take some value, we'll call that x, and it will return 1 divided by 1 plus the exponent, so that's e, a numeric expression representing the power of e, yep, so math.exp to the minus x, that's right. Now, in order to apply that function to each of the cells of the matrix, we made a function for that too. So we can just go hidden will equal matrix dot map. Okay, so it takes the matrix, which is hidden, and the function to apply to it, well, we can use an arrow function here. So x equals greater than x, sigmoid x. So sigmoid x. So that should apply the sigmoid function to each of the values within our matrix. Good. Similarly, so for the second part, find the output values and apply the activation function. It's the same sort of thing. So we can just go let outputs equal matrix dot hidden will be the inputs. So this will be from here, from the hidden layer to the output layer. So hidden will be the inputs and output will be the outputs. So matrix.hidden, this dot weights 1. That's the second set of weights. Outputs, matrix map, so itself, outputs, and apply the sigmoid function to each value. And finally, we want to return those outputs to the sender. The next step, apply bias. I don't want to do that right now, and the reason is because not applying bias can cause issues, and I'd like to see what those issues are. So let's first test this feedForward function. So let's do some console output, console log inputs, and we'll just output the data in the array. So we can use table to that, console.table, inputs.data, and we'll do something similar each step of the way here. So when we work out our hidden neurons, we can just do that. And we'll also want to see what happens after we apply the sigmoid function. Similarly for our outputs. And after the outputs have had the sigmoid function applied to them. So I'll just call that output sig. That will be hidden's sig. Okay, head over to our other file. Let's call that function. So all we have to do is go nn.feedForward. It requires an input array, so something like 0, 1. Now remembering that the number of inputs that we declared for our neural network is 2, so we need to pass an array of length 2 here. Now if we didn't, let's just try that. If we didn't, it should break. We just have to open our file. Open up the console. Yeah, so inputs got through, a single length array, but there's an error. Matrices are not dot compatible. So to fix that, all we have to do is put the second element, put the second input in there. Let's give that a go. Yep, that worked fine. So we've got 2 inputs, 0 and 1. The hidden values are calculated. I'll just believe that. The sigmoid is applied. The output and the sigmoid is applied. Let's just keep resetting that until we get an output that is negative. Here we go. So here's a negative output. Can you see that the sigmoid function has made that positive? So that seems to be working okay. So head over to our other file. We can probably get rid of some of these console logs. So let's just delete a few of them. We'll keep one set. We'll probably need it for our next function. And that is train. Train using input and target arrays. Right, so currently our system doesn't do very much. We give it some inputs and it outputs some randomly generated outputs. Not very useful. So in order to make it do something, how about we create a function that allows us to put in some training data. So we'll call that train. So up inside our class, train, it will take an input array and the target array. So for example, if we had the inputs 0 and 1 and we expect 1 to be the answer, then that's what we would put in here. Let's paste those comments in there. So the first step, feed the input data through the network. Well, we already have a function for that called feedForward. So let's say let outputs equal feedForward, this dot feedForward, the input array. Okay, that's that done. Next, calculate the output errors. Target minus output. Okay, in order to subtract matrices, we'll have to convert the target array first. So let targets equal matrix dot convert. Convert from array. Target array. Okay, good. And let output errors. So we're calculating the output errors here. Let output errors equal matrix dot subtract. And we'll subtract the first, which is the target. So the targets minus the second, which is the outputs. Let's test that. So we'll grab this console data that we kept up here. Outputs, targets, and output errors. So outputs, that'll be fine. Targets, and output errors. Let's print out every step. Okay, head back over to our other file, nn.train. We need an input array, 0, 1, and an output array, remembering it has to match the number of outputs. If it doesn't, we're going to get an error. We'll just give that a go. We'll put a 2-column one there. Okay, so error matrices are of different dimensions. So when it tried to subtract them, it failed. So we'll just put that to a single one. Right, so we have our outputs, which is 0.639. The expected, the target is 1, so the difference is 0.36. That sounds correct. So on to our next step. Calculate the deltas, which are equal to the errors times the derivative of the output. So the derivative of the output is actually the derivative of the sigmoid function. So let's update our sigmoid function to handle derivatives. How about we just pass a flag, deriv equals false. We'll give it a default value so that you don't have to provide it, and if you don't, it'll just return what we always have. If deriv, then we'll return the derivative. Now the derivative of this is x times 1 minus x. That's not the true derivative of the sigmoid function, but we've already applied the sigmoid function, so we don't want to return the true. So I'll put a note here, where x equals sigmoid x. Right, so the true derivative is the sigmoid x times 1 minus the sigmoid x, but we've already applied it, so this will be a good representation, x times 1 minus x. So let's create a variable, let output derivs equal, we can use our map function to apply this, matrix.map, the outputs, and the function will be, we can use an arrow function again, will be the sigmoid x, but this time we'll set the deriv flag to true. So it'll apply the derivative to each of these outputs and assign it to that. And finally, output errors, no, calculate the delta. So output deltas is what we're trying to find here. Output deltas will equal matrix dot, so errors times derivative, so multiply. We can use our multiply function. The first one is the errors, output errors, and the second one will be the output derivatives. And we'll just copy this console log here so we can test this. Output, just the deltas will do. Output deltas. Let's test that. Just run it again. So we have outputs, targets, output errors, and output deltas. Who am I to refute that? It looks okay. Okay, on to the next step. Calculate hidden layer errors. So it's the deltas dot the transpose of weights 1. Right, so let's calculate the transpose first. So we'll call that weights 1, capital T for transpose. Will equal, we have a function for this, matrix.transpose. It just takes a single matrix, so that'll be the this.weights1. Okay, and then we'll need to calculate the hidden layer errors. We'll call that hidden errors. Hidden errors will equal delta dot. So matrix dot, what was the first one? The deltas dot the transpose. Okay, so that'll be the output deltas dot what we just worked out, the transpose there, weights 1t. Again, let's output some, just to make sure it's not throwing an error basically. We don't really know exactly what we're after here. The hidden errors is what we'll want to output here. Hidden errors. Let's give it a go. Right, so we get some output deltas, and then we get the hidden errors crossways. That looks to be okay. So the next step, calculate the hidden deltas, errors times derivative of hidden. Sounds very similar to what we've done up here, so let's just copy and paste that. Let hidden derivs equal matrix map hidden. I just had a thought, we don't actually have visibility to hidden here. Hidden, because hidden was used within this feedForward function. Here we go, let hidden equals that. So how about, instead of creating a local variable here, we use a property on our neural network. We'll say this dot hidden, this dot hidden. So anywhere we use hidden inside here, we'll go this dot hidden, this dot hidden, this dot hidden. And we'll have to go create a property on the neural network. So we can do that easily enough. Just at the top of it, this dot underscore hidden will just equal an empty array. And we'll have to set up some getters and setters for it so that we can access it. Get hidden, we'll just return this underscore hidden, and set hidden, just pass a variable called hidden. This hidden will equal hidden. That should access, yep, that's the same as that. Right, so that should all work in our feedForward now. And back down where we have, back in the train function, where we have hidden here. So hidden derivatives equal matrix map this dot hidden. So we're accessing the actual hidden values at this point in time. X, sigmoid x is true. Yep, we're applying the derivative of it. Calculate the hidden deltas. So the hidden deltas, matrix multiply the hidden errors times the hidden derivs. Right, so let's output those hidden deltas. Let's give it a go. So we have some hidden errors with some hidden deltas. Good. Now for the final step in our little neural network, update the weights. So we have to add the transpose of layers dot deltas. So we add that to the weights. Okay, so let's first calculate the transpose. So let hidden transpose equal matrix dot transpose this dot hidden. Sorry. Next, we have to add the transpose to the weight. So this weights, the associated weights is 1. It's the second set of weights. Will equal matrix add itself. We have to add to itself. So this weights 1. The layer, the transpose layers dot deltas. So matrix dot the transpose, hidden t, and the deltas, which will be the output deltas are associated with the hidden layer. So output deltas. Now we have to do a similar thing for the first weight, so weights 0. So we need to calculate the transpose of the inputs. So inputs t, well, matrix transpose do we have inputs? Do we have visibility on inputs? No, we don't, because again, within the feedForward, we're converting it there and keeping it as a local variable. So there's a couple of things we could do. We could just convert it again within our train array, but we have to remember that this train function will probably be called like thousands of times, if not hundreds of thousands of times. So it's probably better just to assign it to how we're doing with the hidden here. So let's do that. This dot inputs, and we'll have to go up and create a property, same as what we've done for hidden. So this inputs will just equal an empty array, and we have to create we have to create a getter and a setter. Get inputs, return this inputs, set inputs inputs equals inputs. This inputs will equal inputs. That's looking good. So our feedForward function should work now. We're just assigning, instead of creating a local variable, we're just assigning it as a property. Now down in our train function, this inputs should work now. That's fine. And we're updating weights 0 at this point. Weights 0, weights 0, dot the inputs t, and the deltas that are associated with that are the hidden deltas, the next layer deltas. Let's run that, make sure that it's not broken. Okay, it's not breaking, so that's good enough test for me. I think we should actually try this training and see if it actually works or not. How about we get rid of all these comments first, because they're just not, we don't want them printing out every iteration when we've got like 1,000 or 10,000 iterations. Remove all them, remove all them. The weights are updating, great. Go back to our other file. Right, so we'll be calling train, but we'll want to loop over the number of training samples that we have. So we can go for, I'll title this train the network. For let I equal 0, I is less than, say, let's set up a flag for this, so num samples, I++. In there we'll do our training for something. Number of samples, let's go up and create that now. Num samples, I'm not exactly sure how many we'll need, but let's start at, say, 1,000. I know in other examples there's 10,000 and 100,000 and so on. We'll start with 1,000. Num samples is 1,000. And how about we use the classic example to test neural networks is the Xor Gate, the exclusive OR gate. So we'll call this a test Xor Gate logic. Let's take a look at that. Xor Gate, here it is, just this table down here. So when you have two inputs, 0, 0 output 0, 0, 1 or 1, 0 output 1, and 1, 1 outputs 0. So 0, 0, 0, okay, let's write that in here, I think. 0, 0 equals 0. 0, 1 equals 1. 1, 0 equals 1. And 1, 1 equals 0. So only when there's one of them flagged will it be 1. Otherwise, when they're both the same, it'll be 0. So let's create some random input. We'll create 1, 0, 1 there, and 1, 0, 1 there. So we'll input 1 and input 2, or input 0 and input 1. Input 0 will equal, well, it'll be a random number, and we want to round it. So math round just rounds to the nearest integer, and we want to round a random number, math random, which is a number between 0 and 1. So that should produce a 0 or 1. Similarly for input 1, so we can pass them into our training array here. So input 0 and input 1. And we also need an output. So let output equal, well, what's the logic behind it? If input 0 and input 1 are the same, then the output is 0, right? Otherwise, the output is 1. So we can just do a conditional here. Input 0 equals input 1. If that's true, the output is 0, else the output is 1. That's the Xor Gate logic. And put our output into this array here, output. So basically we've created a whole bunch of random training data with the correct outputs, fed it into our system in the hope that it's going to create an accurate prediction. So let's test it. Test output. We can just use the console for this, I think. Console log, we'll put in each of the combinations of inputs. So 0, 0 will equal, let's feed it into our system to get a prediction. Feed forward, we need the array, 0, the input array, 0, 0. and we want to output to the screen the data of that. So do that for each of the possible input combinations. So 0, 1, 1, 0, and 1, 1, 0, 0, 0, 1, 1, 0, and 1, 1. Let's give that a go. Okay, 0, 0's, we're expecting a 0 here and a 0 here and a 1 here and a 1 here. It could be that we haven't got enough samples, so let's try it by bumping up the number of samples to say 10,000. That's looking pretty good. That's close to 0, that's close to 1, that's close to 1, that's close to 0. Let's just keep trying, make sure there's no discrepancies here. Now I have read that not having bias can cause an issue in these situations. So let's see if it comes up with a strange reading on occasion. So here, for example, the prediction for 1, 1 is 0.5. So that could be because of the bias not being there. So I think for safety we should put the bias in. So first of all, what is bias? Well, here's a diagram. Basically we have our input neurons. We just add an extra neuron for bias. It always takes a value of +1, and we add it, and all it does is output its own weights, in effect. It doesn't take an input of any kind, it just outputs its own weights. We'll have one bias node on the input layer and one bias node on the hidden layer. The reason we do this is because the input neurons could take all zeros. For example, in our Xor Gate logic, if we have 0, 0 as our inputs, can you see that that could skew the results? Because 0 times any of these weights will be 0, so it's not going to behave correctly. So that's why we add this bias node. Head into our other file, go right up the top. In the same way that we've created weights here, let's create a bias 0 and a bias 1. So bias 0 will equal a new matrix of just a single row, so one row. The number of columns will be the number of hidden. And bias 1, same sort of thing, one row, but the number of columns will be the number of outputs. Okay, and we'll have to randomize in the same way that we've randomized the other weights. We'll randomize the bias. So bias 0 random weights. Do that for bias 1 as well. Okay, that looks good. Head down to our feedForward function. We've left a node here, apply bias. To apply the bias, all we have to do is, before we apply the sigmoid function to the hidden layer, we can just apply, we can add the bias. So this hidden will equal matrix add this hidden, so adding to itself, this bias 0. So that is applying the bias. Apply bias. And in the same way, we'll do that with the output. So before we apply the sigmoid function, instead we'll be doing it to the outputs. So outputs will equal matrix add outputs, this bias 1. Now down in our train function, we've left a note, update biases. Now all we have to do there is go, in the same way that we've updated our weights here, we'll do the same thing. This dot bias 1 will equal matrix add this dot bias 1, and we're adding the deltas, the output deltas for this one. Same sort of thing for the bias 0, except that we'll be adding the hidden deltas. So this bias 0, hidden deltas. So let's test that. Oh, we have an error. M1 is undefined. Okay. M bias. Maybe. No, I didn't create the getters and setters for these private. So let's do that now. That was a bit silly. So just as we get and set the weights, let's get and set the bias. So bias 0, this bias 0, set bias 0, and this bias 0, just past the bias. Oops. Bias. Okay, so get bias 0, return this bias 0, set bias 0 bias, this bias 0 equals bias. Do that for bias 1 as well. Just update that to 1, 1, 1, and 1. Okay, that should be okay now. Let's give that a go. Great, so if we run that a few times, my hunch is that it will be fine. We'll get a value close to 0, a value close to 1, and finally a value close to 0. And that will do us for this tutorial. So today we implemented our neural network and we tested it by using Xor Gate logic, and it seems to be working quite well. So in our next tutorial, I'm hoping to input our game data, use our neural network magic on it, and output the correct turn direction for our little ship. So this little ship will hopefully turn to the nearest asteroid and shoot it. And that will probably be the last tutorial, so I'm looking forward to it actually. Until next time, see you then, bye!